two projects. In this video, we are going to explain about the project that is Ischemia Heart Disease Prognosis, a hybrid residual attention enhanced LSTM model. So before getting into the execution, first let us understand what is this project about. Ischemia heart disease. Many of them call it as coronary artery disease. It is actually the one of the main reasons people die around the world. What happens is that arteries that carry blood and oxygen to the heart start getting narrow. That is usually because of fat deposits. When that happens, the heart doesn't get enough oxygen. So, this lack of oxygen can cause chest pain, which doctors call it as angina. In worst cases, it can lead to a heart attack and sometimes even sudden death if not treated on time. That's why World Health Organization says that heart-related problems are responsible for almost one third of all the deaths globally, and IHD is a big part of that. So, the important point here is that catching it early can make a huge difference. If doctors can diagnose it in time, patients can get the right treatment, change their lifestyle, and also reduce the chances of something serious happening. So, timely and accurately diagnosis really saves the lives. Even though IHD is a serious condition, one of the tricky thing about it is that it is not always easy to notice early on. Sometimes people have what is called silent ischemia, where the heart isn't getting enough blood, but they don't feel any symptoms. So they might think everything is fine, even though their heart is at risk. Usually, doctors they check for heart problems like stress tests by using stress tests, ECGs, or basic risk assessments, which are helpful. But they can't always pick up the all hidden patterns in the patient's data. This means that sometimes heart disease is detected late or even misdiagnosed, which can be very dangerous. That's why we really need a better and more accurate prediction systems, something that can look at the patient's data and spot people who are at risk early on. If we can do that, it can prevent serious complications and ultimately reduce the huge impact heart disease has on healthcare systems worldwide. So, the system we are proposing is called Hybrid Residual Attention Enhanced LSTM, that is HRAE LSTM model. So, we call it as HRAE LSTM in short. Basically, it is a smart computer model that is designed to predict ischemic heart disease more accurately. So, this works by it works by using a model called LSTM. Two powerful techniques. First, there is LSTM, which is really good at understanding sequences of the information like a patient's medical history or health monitoring data over time. Then it uses something called residual attention learning, which helps the model to focus on the most important information. That is called residual attention learning, which helps the model to focus on the most important information while ignoring unnecessary details. By putting these together, the system becomes much better at spotting patterns that could indicate heart disease. This means it can give doctors more accurate and stable predictions, helping them making better decisions for patient care. So first, we we start with the data. We understand heart disease data set from the UCI. Naturally, like the most real world data sets, some information is missing. So we use a technique called fuzzy based multiple imputation. So here we will be using fuzzy based multiple imputation to fill in those gaps in a smart way, making sure that data is reliable. So missing values will be imputed by using this fuzzy based approach. After that, we normalize or scale the data so everything is on the same level before training the model. Then next comes the model architecture. Here, the model itself has two main parts. The first part is LSTM, which is really good at understanding sequences like a patient's medical history or health monitoring data over time. This helps the model to see the trends and patterns in how the disease develops. Then we have residual attention learning, which acts like a spotlight, helping the model to focus on the important features and ignore irrelevant noise. The residual connections are that is, they make sure that the model can go deep without losing important information. Then comes hybrid mechanism. So in this step, two parts work together in a hybrid mechanism that is LSTM and residual attention learning. The attention and residual connections combined help the model not only spot the areas in the heart disease that may be affected, but also distinguish between healthy and problematic patterns more effectively. Finally, we train the model, that is the data set is split into training and validation sets, and we optimize parameters like learning rate, batch size, and number of training cycles. Once trained, we evaluate the models using accuracy and loss to check how well it is performing. So overall, it is designed to look at complex heart data intelligently, focus on what matters, and make accurate predictions about heart disease. And as an extension to this project, we have added few more features to make predictions more accurate, understandable, and user friendly. So first comes the advanced model, that is advanced machine learning models. So along with the other models that we have developed, we are using XGBoost, which is a very powerful prediction algorithm. And a voting classifier. The voting classifier actually combines multiple models, that is AdaBoost with decision trees here, bagging with random forest, and XGBoost, and then averages their predictions using something called soft voting. This approach makes the overall system more accurate and robust because it combines the strengths of different models. Second, that is in the next case, we made the system more interpretable by using explainable AI techniques. We use LIME and SHAP, which helps to maintain how the model is making its predictions. In simple terms, these methods show which features of the patient's data are influencing the prediction the most. This is really important in healthcare because doctors need to trust the model and understand its reasoning. Coming to the part of frontend, we have developed frontend using Flash framework. Users log in securely, input patient information, and get predictions directly from the trained models. The interface is simple and accessible, so even non-technical users can use it. So these extensions make the system not just powerful but also understandable and easy to use. Moving on to implementation, to implement this project, we have followed the steps which are mentioned in the flow of work. So let's understand how we have implemented the project. First, we will bring in all the necessary libraries and tools we need for data handling, visualization, model building, and evaluation. Then we use heart disease dataset from UCI repository and take a look at the data to understand what features it contains and what target variable it is. Then we do data visualization. So here we check the distribution of target values to see how many patients have heart disease versus those who don't. And we also create a correlation matrix to understand how different features relate to each other. Then comes pre-processing. So at this stage, we remove any duplicate records to keep the data clean, apply label encoding to convert categorical features into numbers that the model can understand, and handle missing values using fuzzy-based multiple imputation to ensure that the data set is complete and reliable. Then comes data splitting part. At this stage, we divide the data set into training and testing sets in 80 is to 20 ratio. The training set is used to teach the model and testing set is used to check how well it performs. Coming to model building and training, here we build various models, including traditional machine learning models and the proposed model HRAE-LSTM and the extension models. Then all the models are evaluated based on accuracy, precision, recall, and reference code, and that performance is visualized through graphs. And we will be saving best performing model for the future use. Then comes interpretability. As the extension, we are using Lyman Sharp to explain features that influence the predictions most. This makes the system more transparent and trustworthy for the doctors. Moving on to the front end part, here the user interface is developed using Flash framework, which includes user registration and login features with SQLite database that supports to store user information securely. And in the next step, that is generally users, they will be giving feature values in the front end that will be pre-processed at the back end. It will be fed to the trained model and trained model will be predicting whether the person has heart disease risk or not. And these are the algorithms used in this project. So this is the proposed model that uses hybrid residual attention enhanced LSTM, and these two are the extension models. So voting classifier is combination of these models. Moving on to requirements to implement this project, basically we need two kinds of requirements. One is hardware and software. In hardware, we need operating system of Windows, processor of 5 and above, RAM of 8 GB and above, and hard disk of 25 GB and above. Software requirements are application of Anaconda, primary language of Python, front-end framework of Flask, back-end framework of Jupyter Notebook, database of SQLite 3, and front-end technologies are HTML, CSS, JavaScript, and Bootstrap 4. So this is the overview of the project. Now let's execute. To execute, open the code folder that contains source code files. So let's open it. So these are the source code files. Let's understand. In this folder, we have the dataset that is used in the project. And this is the model folder in which we have algorithm information that will be loaded into the project code during runtime of the application. And here we have static folder in which we have CSS, JavaScript, and Bootstrap files which are important for this that is project's visual appeal. And here we have templates folder in which we have HTML pages used in this project. It typically includes files like index.html, about.html, etc., which represent different pages of the website. And in this, we have test cases that we will be using in the front end. And here we have app.py file. So this .py file, it contains the information related to front end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in HTML templates. And here we have notebook file, which is a Jupyter notebook file, and it contains a combination of code, graphs, and outputs all in one piece. It allows users to write and execute code in individual cells, making it a popular choice for the data science. And here we have signup.db file. This file is a database file which is used to store the user information. So this is all about the code folder. Now let's execute. So copy the path of the code folder from the address bar of the file explorer. I'm copying it. Now open Anaconda prompt. So it is open. Now give the command cd, give the space, paste the copied path, and now click on enter. Here, if you observe, current directory is changed to the code folder's path. Now compile app.py file by giving the command python space app.py and click on enter. This command will execute Python script and perform a runtime check for any syntax errors or logical issues. And after running the Flask framework, that is after running the app.py file, Flask framework will host the application locally at the default address, which is the localhost and the port, unless configured differently. So this is the localhost and this is the port. Now copy this local link provided by the Flash framework and paste it in any web browser. I'm copying the link. I prefer Chrome, so I will paste it in that. So paste the link here, click on enter. So this is the web page of the project, which is displayed in the browser, and this is developed using Flask framework. So this is the web page of the project. So first you need to get registered. So click on register and create an account. I have already created, so I'll directly sign in. To create an account, you need to fill in all these details. Now let's sign in. Give your username and the password. Now click on sign in. We have signed in successfully and redirected to the prediction page of the project. So here you can see parameters, right? So user needs to provide this information about the patient. So these inputs cover basic details, heart function, blood tests, and exercise related measurements. Let's understand them. So the first parameter we have is the age. That is the basic information. So patient's age in years. Age is key factor because the risk of heart disease increases as people get older. Then we have gender. So gender is male or female. Gender can influence heart disk, that is heart disease risk and symptoms. Then we have chest pain type. So this is the kind of chest pain that the patient experiences. There are different types. Some indicate higher risk than the others. Then we have resting blood pressure. So it is the blood pressure measured when patient is at rest. High blood pressure is a major risk factor for the heart disease. Then we have blood analysis. So this is the serum cholesterol. So this is a cholesterol level in the blood. High cholesterol can cause artery blockages. Then we have fasting blood sugar. It is a blood sugar level after fasting. High sugar levels may indicate diabetes, which increases heart disease risk. Then we have ECG heart rate. So here in this ECG heart rate, we have two different types. That is resting ECG results, that is electrocardiogram reading while resting. Abnormal results can indicate heart problems. Then we have maximum heart rate. It is the highest heart rate achieved during the activity or exercise resting. Then we have exercise information. So here we have exercise induced angina. It is whether the patient experiences chest pain during exercise, which can indicate restricted blood flow. Then we have ST depression, that is old peak value. It's a measurement from the ECG showing heart stress during the exercise. Then we have advanced parameters, that is ST segmented slope. It is the slope of ST segment in the ECG during peak exercise. It helps to indicate heart function. Then we have major vessels. It is a number of major vessels that seen in the imaging that are affected or blocked. Then we have thalassemia. It's a genetic blood disorder that can affect the heart rate, that is heart health. So this is all about the parameters. Now let's enter them. So let's open the test cases for that. Open test cases, open sample file. So here, this is the target that we have. Let's apply, no need of applying filter to it. So let's directly enter. So let's try with the first case where person's age is 63, gender is female. So your gender is female. Chest pain type is asymptomatic, and the resting blood pressure is 163. And here, coming to blood analysis, serum cholesterol is 151. Fasting blood sugar is true. That means he has fasting blood sugar. And then ECG. So resting ECG is STT wave abnormality. And maximum heart rate is 189. That is Talach value. Talach's maximum heart rate. And your exang value, that is exercise induced angina, that is no. ST depression is 4.8. And coming to advanced parameters, so here ST sloping is down sloping, so select it. Major vessels are zero vessels, so here you can see zero vessels. And thalassemia, it is fixed defect. Now click on analyze with AI model. So this given information, it will be pre-processed at the backend, it will be fed to the trained model, and then trained model will be giving us a prediction. And here we got the prediction that it is no heart disease detected. Based on the provided medical parameters, our AI models indicates that patient shows no signs of heart disease. And you can even print the results. And here we have recommendations. So here you have recommendations. And here you have model information. That model type is machine learning ensemble model. And this is the analysis date. 13 features, that is 13 medical parameters have been analyzed. And these are the recommendations for the patient. Now let's do the another prediction. So click on prediction. And here, let's start filling the details. Let's try with this case. Here, age is 42, gender is female, and chest pain type is atypical angina. Blood sugar is 166. Blood analysis is, that is serum cholesterol is 193. False is the blood sugar. Resting ECG is false. Sorry, resting ECG is left ventricle hypertrophy. And maximum heart rate is 189. And here we have ST depression, that is exercise induced angina. So this is the, just wait a minute. So here we have 189. So exang value is the exercise induced angina, which is no. And ST depression is downsloping. Sorry, ST depression is 1. And ST segment slope, that is downsloping. So select downsloping. And major vessels are 3. Thalassemia is fixed defect. Now click on analyze with AI model. So here we have prediction that no heart disease detected. Let's do new analysis. So click on new analysis. Now let's check with this case. So the age is 70, gender is male, chest pain type is asymptomatic, and resting blood sugar is 145. Blood analysis is serum cholesterol is 174. Fasting sugar is false. ECG, it is normal. Maximum heart rate is 125. Induced angina is yes. 2.6 is the depression and downsloping. Zero vessels. Thalassemia is reversible defect. Now click on analyze with AI model. And here you can see the prediction that it is heart disease risk has been detected. So the model has identified potential heart disease indicator based on the provided medical parameters. You can even print the results if you want. So let's check with the last case where age is 60 years, gender is male, chest pain type is asymptomatic, resting blood sugar is 130, serum cholesterol is 206, fasting blood sugar is false, ECG heart rate is left ventricle, and here we have maximum heart rate that is 132, and exercise induced angina that is yes, 2.4 is the slope, that is ST depression, and then we have ST segment slope that is flat, number of vessels are 2, thalassemia it is reversible defect. So click on reversible defect. Now click on analyze with AI model. And here if you observe, we got the prediction that heart disease risk has been detected. And you can even print the results if you want. So this is how you need to do the detection. Now let's check with the graphs. Click on graph. And here we have the sample outcome graph where on x-axis we have the target and on y-axis we have the count. Now get back. Click on graph. Here we have confusion matrix. So this is a confusion matrix. And here we have SHAP impact on model output. And here we have accuracy comparison graph. This is the accuracy comparison graph, where on x-axis we have all the models that are trained and on y-axis we have extension. And here we have FN score. This is the FN score, recall score, precision. This is the precision score. And here we have sensitivity. This is specificity. And here we have MCC. So this is the MCC score graph. Now click on logout. So the system helps to identify people who might be at risk of the heart disease early on. So they can get timely care and make lifestyle changes. By doing this, it can save lives and make heart health easier to manage for everyone. So this is all about the project.
Thank you for watching video. For more projects please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.